So, notes today are going to be on your own, okay? So in your notebook today, but then this weekend you have, well, I shouldn't say this weekend, sometime before your class on Tuesday, you have a video to watch. That video's notes are in your note packet. Okay? So today, on your own, the video that you have to watch over the weekend or Monday, in your notes packet. That video is already posted on Canvas. It'll be posted even better with more like flashing lights and stuff. Look at me in a little bit. Okay? So, here we go. Warm up. Okay? Newsmeyer Farms bought a new tractor for $192,000, which, by the way, if you can find a brand new tractor that size for $192,000, buy 4 of them. Okay? Because that's how much it really costs. Okay? Right? Just so everybody knows, so everybody's clear. That's probably a $570,000 tractor. Brand new, 0 hours on it, fresh off the assembly line. Okay? All right? So find me how much my tractor is worth in 14 years. What are we talking here for terms of an equation? Let's go. The price of my tractor after T years is how much? What's my equation? 192,000 is what we started with. Yep. Depreciate, is that going up in value or down in value? Down in value. So what's my B value, my rate? 0.95? We're going to take that to the T. We want to find P of 14. I get $93,633 and I think it rounds to 60. Yep, 60 cents. Yes? Yeah. Cool. Next slide. Shade this slide. There we go. Shade. Okay. So exponential growth is unbounded, right? It's going to keep growing and growing and growing and growing and growing and growing forever, right? Now, in some cases, that's fine. But in other cases, like for instance, yesterday we did an example about the population of San Jose, California. Okay? And we came up with an exponential function to represent the population after T years after, I believe it was 1990. Okay? Does anybody see an issue with that? Who said yes? Yeah.
Eventually it's going to be too big.
Like there's going to be too many people in that little space?
Yeah.
Yeah, like if you think of Wausau, like think of Wausau as San Jose, okay? Right now Wausau's got, what, 40, let's say 45,000. Okay? Comfortable, right? Okay? Same size town, but now with 1 million people living in it. Okay? Way too many, right? Like there's not going to be enough space for everybody, right? Okay? So sometimes exponential growth is needs to be, quote, reined in. Okay? So another example, would be, what was it, the iPhone 15 is coming out soon. I don't think it's come out yet. Okay? But that's going to take off like a rocket, right? As soon as it comes out, everybody's going to want one. Happens every time the new iPhone comes out. Okay? Everybody's going to want one. So sales are just going to go, they're going to spike. But then what's going to happen? They're not going to go back down. They're going to level off, right? Because sooner or later, like let's say a year from now, the people that want an iPhone 15 are going to already have an iPhone 15 and not going to have to go buy another one. So sales are going to kind of level out. And so we have those scenarios, and the way that we can get around with those, when there's a limit to the growth or a limit to the population that can happen, we have a brand new function out there called a logistic function. And so we're going to learn all about logistic functions today. Okay? Logistic functions start out and they grow exponentially. Kind of like we were talking about the sales of the latest iPhone. They grow exponentially. Okay? But then they got to level out. And there's a limit to that. Okay? So a logistic function has in it a lower bound. Okay? So it's got a lower horizontal asymptote. Typically, that is y equals 0. Okay. It also has an upper bound, an upper horizontal asymptote. And we call that one the limit to growth. So we got a lower limit, we got an upper limit. And that whole function is going to live in that little zone. Okay? And how it looks is, if it's a logistical growth, it's going to start out really close to the lower limit, and then it's going to grow exponentially, and then it's going to turn, and it's going to approach the upper limit. So it'll never get any bigger than that upper limit. That upper limit is there. That's a ceiling. Okay? We're not going to be able to punch through that ceiling. A hard ceiling. Okay? There are two different forms of logistic equations, or logistic equations, I should say. The left one is the one that you're going to use the most, okay? Because it uses the a, b to the x one. The right one deals with e. You'll use it occasionally, but most of the time you're going to use the left one. When we are creating our own, when we're creating a logistic function, we're going to create the left one. We're not going to create the right one. Okay? So C is that limit to growth. You're going to have a number in your numerator. That's your limit to growth. That's as big can be. Okay? So in an example, I don't know, I'll make something up here, like in Wausau, the population could grow to, let's say, 125,000. That would be our limit to growth. That would be our C value. Okay? A, B, C are all positive. K, and the other one is positive, but when you utilize it in this one, K is negative. Okay, so that negative is there, but K is positive. If for here, for a growth, B is between 0 and 1, if it's a logistical decay, B would be bigger than 1, or K would be negative. That would be your decay. Okay? So we want to make a logistical function with the following conditions. We've got a limit to growth of 60. We've got an initial value of 12, which means we go through the point 0, 12. Our y-intercept is 12, however you want to say that. And our curve passes through the point 1, 24. Okay? So we want it to look like y equals c over 1 plus a b to the x power. Right off the start, from those three, do I know any values? What? C is how much? 60. C is 60. Yeah? So right from the start, my function is going to be 60 over something. Okay? If you have the initial value, let's utilize that. Okay? So 12 is my initial value. I know that 60 is my limit to growth. I know that this bottom is going to be 1 plus a times b to the x power, but what is my x? My x is 0, y is 12. And that helps us. What is b to the 0 power? 1 times a. A. So this is just 12 equals 60 over 1 plus a. How do I solve that? Cross multiply. So I get 12 times 1 plus a equals 60. How? Could distribute, or I can just divide both sides by 12. Get 1 plus a is 5. So a is 4. So now I know that a is 4. Okay. Now we got to find b. So I'm going to utilize my point here of 24 is now going to equal 60 divided by 1 plus 4 b to the, not to the 0 power, to the first power. Yep. That's going to be 1 plus 4b then down there. How are we going to solve that one? Same way, cross multiply again. Okay? So 24 is going to equal, oops, excuse me, not 24 is going to equal. I forgot the 24 times 1 plus 4b is going to equal 60. Divide both sides by 24. 1 plus 4b is going to be 60 divided by 24 is 5/2. Subtract 1 from both sides. 4b is going to be 3/2. Dividing by 4 is the same as multiplying by 1/4. 3/2 times 1/4, 3/8. So 3/8 is my b value there. Okay? Let's graph that. Okay? So start yourself a brand new graph. Because we're inputting a fraction, our function is a fraction, I would start with a fraction bar. To put a fraction in anywhere in the graphing calculator, it's Control Divide. And it sets up your fraction for you right away. Your numerator then is going to be 60. Your denominator is going to be 1 plus 4 times, now here, because that b is going to be to a power, we're going to put it in parentheses, 3 divided by 8 raised to the x power. And when you hit enter, you'll see it, but you don't see the whole thing. So let's adjust our window. -10, good for the x's? I think so. Maximum on the x's. For the x's? We can. So let's go out to 50. Okay? Good on the y minimum?
Yeah, we can go put in like -2.
Okay. I would go at least -5. Just because you're gonna see it. I like seeing it. Maximum. Why maximum? That one would be 70, because we gotta get at least to 60, right? Yeah. So we can see that top. Then when we hit enter, there it is. Okay? And there's our graph. Starts out and grows exponentially, and then levels off and slowly increases. Good stuff. Okay? What I would like you to do now is I'd like you to find me this logistic function. So we know our limit to growth is 30, right? So right off the start, y equals, we're going to have 30 up top. We know the bottom's got to be 1 plus a b to the x power. Okay? So 0, 5. So that means that would be we went blue. Blue 5 is going to equal 30 divided by 1 plus a times b to the 0 power. B to the 0 power is 1, So really that's just 1 plus a down there. So then this would be 5 is equal to 30 over 1 plus a. 5 times 1 plus a is 30. 1 plus a, then it's got to be 6. So a has got to be 5. We agree with a being 5. Yeah, okay. Then let's go to the next one. The next one has 15 equaling 30 over 1 plus a is now 5. B cubed, correct? Yes? Okay. 15 times 1 plus 5b cubed is equal to 30. Let's divide both sides by 15. 1 plus 5b cubed is 2. Subtract 1. 5b cubed is 1. Divide by 5. B cubed is 1/5. How am I going to solve that? Cube root. So b here is the cube root of 1/5. Now, ideally, you're going to leave it like that because that's exact. Okay? If you round it to If you round it to 0.5848, whatever you round it to, then that's going to be off by a little bit when we're doing our calculation. Okay? So here, I would write this as y equals 30 over 1 plus 5 times the cube root of 1/5 to the x power. Okay. All right. Now, got plenty. Second time through, plenty of time. First class, I only have 3 minutes to do these next 2 slides. And you may be saying to yourself, how are we going to get it done? Just that good. Okay. Now we got to graph these things. Okay. So let's graph a logistical function. Well, we already know one of the 2 horizontal asymptotes. It's y equals 0. Okay? So we can put that on our graph right off the start. Do we know the other one? What is it? Y equals 8 on this one. Because that limit of growth up here, that's going to be our upper horizontal asymptote. Okay. We know it's going to start out because it's a growth, because this is between 0 and 1 right here. That's between 0 and 1. So we know it's a growth. So it's going to start out low, and it's going to come shooting up. Really, only one that the easiest point to graph is going to be that y-intercept, that 0 value, that initial value. How do we find it? Put 0 in for x. Put 0 in for x. If I put 0 in for x, what happens to the 0.7 to the x power? Goes away. Okay. So I'm left with 8 over 1 plus 3. What's 1 plus 3? 4. What's 8 divided by 4? 2. So my y-intercept for this problem is 0, comma 2. Which is, so here would be 4, so here would be 2. There's the graph. Okay. Just that easy. Logistical graphs are the easiest of easy graphs because it's gotta live in that zone. Has to. Doesn't get any choice but to live right in that zone. Okay? So, talk to me. Last example. Quick graph. Even though this one's an E, we can still do it. Quick graph. Horizontal asymptote where? Y equals 0 for sure on one, and y equals 20 on the other one.
Is it always y equals 0?
Yep.
Because there's no plus or minus.
Yep. There's nothing, there's no plus or minus afterward. If there is a plus or minus afterwards, then that whole zone gets shifted, that whole thing. So both of them would get shifted. Okay? Y-intercept. This goes away, right? Oops. Hold on. This goes away, right? So 20 over 3, right? Okay? So we got this whole thing. We divide it into thirds because this whole thing is 20. So we divide it into thirds. So my y-intercept is this. Okay. Good. Remember, you have a video to watch online on the Canvas this weekend.